second order system is in this form. It's typically in this form. Is d square y of t by dt square plus 2 zeta omega n d y of t divided by dt plus omega n square y of t is equal to omega n square u of t. So this is the typical time domain equation of a second order system. So you can see that the highest order of the derivative is 2. So it is a second order system only. And compared to first order system, you can see two new parameters here. One is called zeta. Zeta is called damping ratio of the system. Now I will define all the parameters. Later we will see what it is. Okay. Omega n is called natural frequency. Natural frequency. And actually damping ratio is a unitless factor only. Natural frequency unit is radians per second. Okay. So first of all, you can obtain the transfer function for this system. So in order to that, taking Laplace transform, keeping all initial conditions 0, we can write s square y of s plus 2 zeta omega n s y of s plus omega n square y of s is equal to omega n square u of s. Okay, we will see later why this omega n square is sitting closer to the u of t, right? Previously you used to take u of t only, right? But in this case we have multiplied that time omega n square with u of t, right? So rearranging this equation, we can obtain the transfer function of the second order system. So we can write like this: t of s is equal to y of s divided by v of s is equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. So this is the standard form of a second order system. Second order system. The standard form of a first order system, how it will look like? 1 divided by 1 plus st, where t is the time constant. But for a second order system, it is omega n square divided by s square plus 2 zeta omega n plus omega n square, where zeta is the damping ratio of the system, omega n is the natural frequency, radians per second. And we will see what is zeta and omega n detail. Okay, so in order to for the system to be stable, for stability, these omega n and zeta, these are the two factors, right? Omega n should be greater than 0 and zeta also should be greater than 0. Then only the system is stable. If zeta is going to negative, omega n is also going to negative, means your system will become unstable, right? Because poles will move to the RSP of the plane. Okay, this you keep in mind. Now, how to solve the poles of the system? We know n is equal to 2, m equal to 0. Since n equal to 2, it is a second order system only, and also strictly proper transfer function. So in order to find the poles, what we have to do? We have to solve the polynomial, denominator polynomial, right? Denominator polynomial is x square 2 zeta omega ns plus omega n square equal to 0. So what are if you solve this, you can find the poles, right? And it will be like this. Force S is equal to minus B plus or minus root of B square minus 4AC by 2A. If you apply that concept, you will get minus zeta omega n plus or minus omega n into root of zeta, sorry, zeta square minus 1. So we have two poles, one at minus zeta omega n plus omega n into root of zeta square minus 1. The other pole is minus zeta omega n minus omega n zeta square minus 1. This is keep in mind. So the location of the poles depends upon the two parameters zeta and omega n. So this greatly depends upon the zeta, right? It depends upon the zeta value. So we'll see how these poles will vary with respect to zeta. Also, how the response look like with respect to damping ratio. Okay. So you can see that, and we already mentioned that in order to make the system to be stable, zeta value should be greater than 0, right? So we will study some 4 cases here. Case 1, zeta value will be less than 1. It should be 0 less than zeta less than 1. So in this relation, if our zeta value is between 0 and 1, what will be the nature of poles? We know the pole relation is minus zeta omega n or minus omega n root of zeta square minus omega 1. Okay. So in this case, first case, if our zeta lies between 0 and 1, what will be the nature of poles?
Imaginary, sir.
Yeah, because this part is a root of zeta square minus 1. So if zeta is less than 1, it's between 0 and 1, means this part will go negative, and obviously j will come out. So this will become imaginary, right? So in general, we can write if zeta is less than 1, the pole can be written as minus zeta omega n plus or minus j omega n root of 1 minus zeta square. Can I write like this? Because I am taking minus common from here, because zeta is less than 1 means obviously this will goes to negative. So in general, we can write minus zeta omega n plus or minus j omega n multiplied by root of 1 minus zeta square. Clear? So this can be again written as minus zeta omega n plus or minus j omega d. Okay, we will see omega d later. Omega d is called damped frequency. Now one more time is coming, right? Previously it was omega n, it is the natural frequency, unit is radians per second. One more time we introduce omega d, it is called the damped frequency, that unit is also radians per second. How will you define omega d? Omega d is equal to omega n multiplied by root of 1 minus zeta square. Right? So this kind of system is called underdamped system. So when if zeta is less than 1, we can call the second order system as underdamped second order system. And if it is between 0 and 1, we can call it as a stable underdamped second order system, right? We already mentioned that if zeta is greater than 0, the system is stable. And if the value lies between 0 and 1, we can call this kind of system as underdamped second order system. So from this analysis, what you understand? For an underdamped system, what is the nature of the pole? It should be correct. So if we draw the poles, how can we draw it? I draw the S plane. Okay. This is the imaginary part. This is the real part. This is S plane. This is origin. So I have a real part and imaginary part, where the real part is negative, right? It is at what value? So it is somewhere here. It will be minus zeta omega n. So my location will be, one pole will be here, one pole will be here. So what is this value? It is plus j omega d, and what about this one? This minus j omega d. Minus j omega d. Right? Clear? Any doubt, please ask. Now we'll move to another case. Case 2. Case 2, when zeta equal to 1. Damping ratio is equal to x at 1. So what will be the nature of poles? If you substitute 1 in that relation, the poles will be there is no imaginary part, right? Yeah, it will be real. And what is the magnitude? Zeta is 1 means it will be minus omega n and minus omega n. Right? So what is the meaning? So if zeta is 1, your poles are equal at minus omega n. Right? Previously it is distinct. We are having distinct poles. Now your poles are equal, and it is having only negative real parts. There is no imaginary part. Negative real parts. So if you are having a second order system and the poles are equal and it is only having negative real parts, the meaning is your system is having zeta equal to 1. Damping is equal to 1. So if zeta is equal to 1, you can call this system as zeta equal to 1. You can call the second order system as critically damped second order system. So if zeta lies between 0 and 1, we can call it as an underdamped second order system. If zeta is exactly 1, we can call it as critically damped system, and it is also greater than 0. So we can call it as a stable critically damped second order system. So if you substitute 1 in this transfer function is omega n square divided by 2 zeta omega n plus omega n square, right? So if you substitute zeta equal to 1, what will be your response? Sorry, your transfer function becomes s square omega n square plus s square plus 2 omega ns plus omega n square. So I can write omega n square divided by s plus omega n the whole square. So from this you can see that we have two poles at omega n minus omega n. So if we locate these poles in this same S-plane, where we can locate it? It is minus omega n, right? Yeah, it will be somewhere here, and we have two poles, right? Two poles at minus omega n. Now we will move to the another condition, case 3. Sorry? Any issue? Presentation is stuck. Okay.
Is it okay now? Okay, then we'll continue. So after substituting zeta equal to 1 in the transformation, we got equal to s plus again square and then located the corresponding force. Now we'll move to the third case. Case 3. Where zeta is greater than 1. So if zeta is greater than 1, what will be the force? Hmm? Is minus zeta omega n plus or minus omega n multiplied by root of zeta square minus 1, right? So it is having two parts, right? One is minus zeta omega n, the other part is omega and root zeta square minus 1. Now, where you will, if you move to the same diagram, is having two poles. One is minus zeta omega n plus omega n root of zeta square minus 1, right? Another one is minus zeta omega n minus root of zeta square minus 1. So basically the second one will stay somewhere here, right? Because it is more negative, right? Both are negative. So this pole will be minus theta omega n minus root of zeta square minus 1. So omega n into root of zeta square minus 1. So where you will locate the other pole minus zeta omega n plus omega n root of zeta minus 1. Here see here zeta is greater than 1, right? So which part will be dominating? See, you have two times minus zeta omega n plus omega n into root of zeta square minus 1. So if zeta is greater than 1, this part will be dominating. Minus zeta plus zeta square minus 1. So if zeta is greater than 1, the negative part will be dominating and correspondingly the other pole the origin. It is zeta omega n plus omega zeta square minus 1. Okay, so the poles are distinct and yeah, there is no complex part in this pole when zeta is greater than 1, and if zeta is greater than dominating, that means it is always negative. So all the poles should always be on the left hand side of the line. So we can call it as a stable system. Now, one more case is there. What is zero? What happens? Zero. What is of the pole? Hmm? minus zeta omega will become 0. There is no real part. What about the other part? It will become plus or minus omega n root of right. So it can be written as plus or minus j omega. Okay. So when zeta is 0, you only have imaginary poles. There is no real part, nothing, right? So all the poles should lie in the imaginary. And we can call this system this type of system undamped system. Anyway, all these things we will see in detail. So we have four cases. When zeta is less than 1, we can call it as an undamped system. The nature of poles, the poles are distinct and having real and imaginary part. When zeta is 1, we can call the system as overdamped system, sorry, critically damped system. In such case, the poles are equal and have only negative real parts. And in case 3, when zeta is greater than 1, in this case also, poles are distinct but real parts, right? There is no imaginary. When zeta is equal to 0, the poles are distinct in nature also. They are complex in nature. There is no real parts, and such kind of systems are called damped system. Clear? Now, now you consider a mass spring damper. You already see this spring dampers.
Sir, your voice is breaking, sir.
Transfer function of is it is okay now? Sorry, I think your voice is not clear for me. Can you put in? Fine. Okay. 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 Then we can. Yeah. So mass damper system. The function of this system, we already seen all those things, right? Anyway, I'm not going to derive it. So what is the transfer function of this system? Y of s divided by u of s is equal to 1 divided by m square plus b k, right? Where m is the mass, b is the damping coefficient, right? So if you compare with the general, I'm taking this m out, I can square plus b by m s plus k by m, right? If you compare this term, it's a second order system, right? Yeah. If you compare the same system with the standard form omega n as omega n square, you can derive both zeta and omega n, right? So what is omega n square? Omega n square k by m. From this, okay, the nature of frequency into root m. How will you find zeta? 2 zeta omega n equal to p by yeah. So on polynomial with second order polynomial, the standard second order polynomial, you can write omega n and zeta. Omega n is obtained as root k by m, obtained as divided by 2 root n k. So our aim is what zeta indicates. See, the zeta is related with system. So this is a question of amount. So what is again? This is a dissipating element, right? Unlike this m spring constant, dashboard represents the dissipating element. So it is an indication of how much energy dissipated in the system. Is another way we can tell is the indication of amount of damping or the energy dissipation in the system. Okay, because line B indicates the damping coefficient. So hope everyone understood what is zeta. Now one more time is there. What is omega n? Right. So omega n is defined as natural frequency. So what is natural frequency? Okay. Suppose this system in this example, mass damper example, zeta damping is not there. Zeta is 0. Zeta is 0. Undamped system, right? Damped system. And consider there is no input. U of t is 0. Initial conditions are not 0. Y of 0 is not 0. Okay. So how can we? So if U of t is not 0, some initial conditions, what is the name of that response? We already mentioned that output response is having 2, right? one is due to the input, that is called forced response, and one is due to the zero, sorry, that is called response. So suppose our dynamic is we don't have any input and our conditions are not zero, the equation becomes y plus omega square y of t, right? So because it is zero. So I'm not going to solve this. What is the value you are expecting here? What is the nature of the response you are expecting? Free response. In Laplace transform, one is there, again omega square is there. So what is the time in y of t? You can expect a sinusoidal outputs, right? Anyway, do it. Take some value. Someone something like that. You said you are y naught of 0 is not equal to 0. Y dash 0 is also not equal, and you do all that. You will get exponential. Sorry, output response where n is the